Hi there. I'd like to welcome everyone to today's webinar involving the mesh generation, simulation, and analysis of a high-energy water injection pump. Everyone's in, all the attendees are in mute mode at the moment, so as we progress through this webinar, if you have any questions or would like, we'd welcome you to type them into the right-hand side. There's a little Q&A box. You can type in questions, and we'll have a Q&A session here at the end of the webinar where we'll go through and field those questions. We'll also be placing the recording of this webinar online. Details for that will be at the end of our presentation here, so you can view this later on. So let me introduce myself. My name is Kevin Colburn. I work for CEI as a representative for Insight. My background is in CFD for about the last 20 years and using Insight over the last 7 years to try to extract out meaningful information from the analysis. Joining us today is also Jeremy Shipman from Craftech. The pump model that we'll be talking about today was developed and run by the folks at Craftech. Jeremy's long experience at Craftech affords him a wealth of experience in using the tools and techniques needed to complete such a complex simulation. And then finally we have Travis Kerrigan from Pointwise. Travis has worked with Pointwise for some years now and is focused on helping users use Pointwise in interactive and automated techniques for gathering and generating the mesh that needed for these CFD analyses. So I'm going to pass control over to Travis here, and he's going to talk to us about how Pointwise was used in this particular model.
All right, thanks, Kevin. Okay, I'm going to talk a little bit about how Craftech utilized Pointwise to generate hybrid meshes for this high-energy water injection pump. So the first step of any meshing process is importing the geometry. And with Pointwise, we can bring in native CAD, CATIA, ProEngineer, SolidWorks, even things like IGES and STEP, and some discrete formats as well. And as you can see, this pump assembly, it's pretty complex, consists of several components. And one of the nice things about Pointwise is you can actually bring in each of these components into the same Pointwise project. So they actually exist in different files. And when you bring in one and then try to bring in another, you're presented with a dialog box that allows you to append to the current Pointwise project. And that's pretty nice because you can have the entire pump assembly existing in the same Pointwise project, and you can work on components individually or simultaneously. So once the geometry is in, the next stage is healing the dirty geometry. And there's a couple different techniques in Pointwise for doing that. The first is solid modeling, and we've talked about this in previous webinars. Simply put, solid modeling is just healing the problems with the geometry on the geometry level. Identifying gaps and cracks in the surface, missing surfaces. We can use a lot of those tools and techniques for generating geometry in the software to heal the dirty geometry. So that's solid modeling. But the approach that Craftech chose to use was another technique that we call fault-tolerant meshing. Fault-tolerant meshing is basically just dealing with the problems in the geometry and just healing over them with the mesh. Okay, so you're presented with the same sort of information but on the mesh level. In this case, we're looking at, for example, connector topology, finding free connectors and things like that. So again, the idea is just leave the deficiencies in the geometry there and just heal over them with a surface mesh. So as I mentioned, this is a pretty complex case. Consists of a number of components or modules, if you will. There's the inlet, the impeller, the diffuser, and the crossover diffuser. And you can mesh them with them all existing in the same Pointwise project. You can mesh them simultaneously or one at a time. And that's kind of how Craftech elected to do things, was use a hybrid meshing strategy to operate on one module at a time. And so, like I said, they chose to use a hybrid meshing approach for this particular case. Now what is a hybrid mesh? Well, a hybrid mesh is basically just a grid that consists of more than one element type. So it's not all hex elements, it's not all tet elements, it's just a mixture of the different element types. Maybe you're generating a multi-block structured mesh in a relatively straightforward part of the geometry, but using an unstructured mesh in a more complex part of the geometry, and that's kind of the idea. And here we're looking at a cut through the actual grid. We've got the inlet sweeping up through the impeller, through the diffuser, around to the crossover, and then turning back into an axial direction for another stage of the pump. And you can even see some of the leakage paths, the impeller leakage paths and crossover leakage paths have been modeled. So it's a very complex CFD model. So there's a number of reasons that Craftec chose to use a hybrid meshing strategy for this particular problem, and one of those reasons is time. It saves a little bit of time, again, like I'd mentioned before, by being able to decide which type of mesh topology you're going to use for a particular part of the geometry. Another reason is the hybrid meshing approach really allowed Craftec engineers to choose the best topology for the physics of the geometry that they were looking at, and not really have to unnecessarily propagate points in topology into regions where you would have poor quality elements. A good example is maybe looking down here at one of the leakage paths. This is a cut through that. There's some hex elements here, but instead of taking that topology and propagating it into the semicircular region, they elected to just use prism elements to resolve that region, nice high quality prism elements. Again, no need to unnecessarily propagate those points in topology into that region when you can use a different type of element to resolve it. Another interesting place to look at is actually one of the diffuser passages. This is a true hybrid block, consists of every element that Pointwise supports. We've got triangles on the surface extruding into prisms. You've got quads on the surface extruding into hexes, a tet core, and then a pyramid interface. So really a truly hybrid block, utilizing a lot of the hybrid meshing techniques in Pointwise to generate this grid. Another benefit to using hybrid meshing is it's somewhat easier to create point mesh interfaces between adjacent modules to improve solution interpolation from one module to the next. And Jeremy's going to talk a little bit about that modular approach in his part of the presentation. So organization is extremely important for dealing with these very complex grid assemblies. And really the power of that in Pointwise is found in the layer manager. The layer manager operates very similar to layer managers in other tools, maybe like Photoshop, where you can isolate a given layer and operate on it, or you can turn on multiple layers and see the effect of some operation on other entities that exist in other layers. And so you can see that, you know, they've layered up the diffuser, the crossover, the impeller. Layer sets are also pretty handy in the software. Basically, we could create a layer set for all the crossover layers, so when we activate that layer set, all the crossover layers will turn on automatically. And here's an example of kind of what layers allow you to do. In this case, they've isolated the layers that allow them to focus on the structured meshing topology in the crossover passage that they're operating on. So again, being able to isolate and focus on a given piece of that geometry, especially when you've got the entire assembly living in the same Pointwise project file. This is how you can get away with something as complex as that. So selection also becomes extremely important. Again, when you can have hundreds, if not thousands, of entities living in the display at any given time, how do you go about selecting them? Now, we've talked about the mask panel before and picking entities in the display window. The mask panel allows you to do very targeted entity-based selection, but you can also do selection from the list panel just outside the display window. Maybe you've named certain entities and you could do a drop down on that entity list. In this case, we're picking blocks by a given name and they're being selected in the display window and we can operate on them. Another thing you can do is create groups. So groups kind of help you organize things, but they're more for selection. You can create a group for the different entity types in Pointwise, database entities, connectors, domains, and blocks. And as the example shows in the back, you know, I've created a group for the impeller blades, so when I select that group, all the impeller blades are selected. I could then maybe modify their display attributes, change their color, or apply a surface mesh to them. So again, just creating a group allows you to quickly select, batch select a bunch of entities, and then operate on them. And then I've highlighted this adjacent select tool because we haven't really talked about this too much in the past, and that allows you to select, you know, one adjacent entity or all adjacent entities based on an angle limit. So another way to do some selection in Pointwise. So the resulting grid for this case was about 10 million elements and consisted of nearly 1,000 blocks. And from what Jeremy told me, it took an engineer less than a week to make this grid, which is pretty impressive because it's a very complex grid system. But not all of it had to be done by hand. In fact, you could save quite a bit of time by using copy, paste, and rotate. Now, it's important to note that a lot of the geometry is kind of repeated. And what do I mean by repeated? Well, you've got the impeller, the diffuser, and the crossover, and all you really need to do is mesh a single passage of each of those machines, and then just copy, paste, rotate it to create the full wheel grid. And again, that saves quite a bit of time when creating the entire mesh. So once the mesh has been created, the last step is to export it to the solver. Pointwise supports over 40 different solvers, but if your solver doesn't happen to be in this list, maybe you have an in-house code. We have a Pointwise plugin software development kit, and the API provides access to the grid model, so you can actually choose to write it out any way that you'd like. And that's actually what Crafttech decided to do. They wrote their own Crunch CFD plugin that shows up in Pointwise. We distribute it with our software, so that allows them to actually generate the grid in our software, set up the boundary conditions for their solver, and then export it to Crunch CFD. So with that, I'm going to pass things over to Jeremy, and he's going to talk a little bit about this application and Crunch CFD. So Jeremy?
Hello everyone. I'm going to talk to you today a little bit about the process of solving this pump case with Crunch CFD. I want to first go over an overview of the Crunch CFD solution process. We have a preprocessor utility called pre-Crunch. Travis mentioned that we have our own plug-in exporter in Pointwise so that we can directly write the grid out into the Crunch CFD format. The pre-Crunch utility also handles other translations into different formats, and as well as the grid and solution partitioning process. The solver itself, we have a graphical user interface that aids in setting up the inputs for the case. And in addition, for a case that involves multiple parts as this, the graphical user interface is very helpful in managing all of those parts. And then finally, we have a post-processor utility which handles exporting the plot data into various formats, as well as some other post-processing utilities. Briefly, an overview of the Crunch CFD multi-physics framework. We have a multidisciplinary framework that involves a number of different solver modules. Currently, we have an incompressible solver for multi-phase and cavitating liquids, which also includes thermal effects modeling for cryogenic fluids. We have an all-speed preconditioned compressible flow solver that includes non-ideal real fluid equations of state, as well as a chemistry manager for chemically reacting flows. We also have a thermal solver for doing heat conduction problems, which can be coupled to the compressible flow solver. And then finally, we have a far-field noise propagation module that we couple to the flow solver to do acoustic analyses. In this pump case, we made use of both the incompressible flow solver as well as the acoustic module. So an overview of the pump case that we're presenting here today. This is a very high energy pump. It's a 19 megawatt seawater injection pump. It operates at 4950 RPM, generating 15 meters of head at 16,600 gallons per minute. So it's a large pump, large flow rate. The primary simulation objectives were, one, to look at cavitation inside the pump. Its the cavitation effect on the performance, and as well as we were investigating a source of noise that was observed during pump operation. So some of the solver features that I'm going to highlight in this analysis, we did both single phase and cavitation modeling. I'm going to show some unsteady features of the flow field that we looked at. with some interactions between the rotating impeller and the diffuser, and then as well as an acoustic analysis of the pump based on this flow solution. This case is presented in much more detail in a ASME paper that I've referenced at the bottom here. You can look to that for more details. So Travis pointed out some of the modularity of the grid generation that was performed. There were basically 4 parts of this analysis. There's a suction inlet, the impeller, there's a diffuser, and then a crossover diffuser that takes the flow from the diffuser and turns it back around into the axial direction. All of those are coupled together. We have a intermodule boundary condition in between each that handles the communication between each of these modules. So each of these solver modules are operating on their own processors, and what that allows us to do, first of all, Travis mentioned some of the benefits to the grid generation. Just to highlight that again, some of the things we were looking at, such as cavitation, that we would expect to see at the leading edge of the impeller blades. It's very important for us to be able to have a very high quality grid in that location without unduly affecting the other modules. So, so doing this in multiple modules allows us some flexibility in the grid topology. And then the other thing that allows us to do is we have the impeller module, solver module is operating in the rotating frame of reference, while the other 3 modules are solved in a stationary frame. So in the middle of the slide here we show, this is a cut through the grid showing all of those 4 parts connected together. We've got the suction inlet in green, which feeds into the impeller in magenta. The diffuser is in orange, and then there's the crossover diffuser is in black here. And you can also see the leakage flow paths that are included in each of those parts, as Travis mentioned. The total grid size of all of these parts together was about 10 million cells. All right, the first feature of the flow solution I'd like to highlight is the cavitation that was done. There were some steady state simulations that were done to look at the general cavitation. You can see that the cavity is a different shape on one side of the impeller than the other due to some non-uniformity coming in through the inlet. An unsteady analysis was done to get a more accurate performance of the pump, and that's what this animation is on the right here. You can see as the impeller rotates around, the cavity on the leading edge of the blade gets larger and smaller based on its relative position in that non-uniform inflow coming in through the inlet. So that was an important feature to capture. Another feature of the flow that we were interested in looking at was the unsteady interactions between the impeller and the stationary parts of the diffuser. This animation is showing a cut that goes through the impeller, and we're looking at contours of pressure. There's a few things that are features I'd like to point out. First of all, you can see that as the blade passes by the leading edge of the diffuser, there's a pressure wave that travels upstream. On my screen, the animation is not rotating very clearly, but hopefully you can see that. Additionally, as the blades pass by the diffuser blade, you can see a low pressure wave that travels downstream through the diffusers. So those are some of the features that we're pulling out. Okay, on the inflow to the propeller, we have, I'm looking at contours of pressure at the inflow to the impeller here. And again, we see the effect of the non-uniform inflow coming into through the suction inlet. You can see there's a generally low pressure on one side of the impeller than on the other. And you can also see the pressure imprint of the blades passing by. Okay, the third kind of area I'd like to point out with this analysis, we did an acoustic analysis of the pump based on the unsteady cavitating solution. This is pointing out several points were placed in the inflow upstream of the impeller, and we're recording the pressure at these points. So you can see there's a strong tonal signal in that pressure history. Looking at a frequency analysis of those pressure histories, you can see the strong tonal nature of that solution. Basically, what we're having is the pump frequency, the revolutions per second is this first tone. The 7 times that is the blade passage frequency of the impeller, and you can see that is the dominant tone showing up in, upstream of the impeller there. And then there's a harmonic at twice that value. What you don't see is the diffuser having 9 blades would be at the 9 times that that frequency, and you don't see that showing up in the pressure signal upstream of the impeller. And that's I'm going to point out later. We did an acoustic analysis of the pump using the far-field noise propagation module. And what I'm showing here is on the left here you'll see the schematic of the pump. You can see this purple plane right at the inflow. Right at the inflow of the impeller. This is the acoustic data surface where we took where the noise propagation module propagates that out to an observer ring, a microphone ring, if you will, further upstream in the inlet. So on that acoustic data surface, we're showing here the sound pressure level contours on that surface for each of the fundamental frequencies that we were looking at. And as you can see, on that surface we don't see a large contribution from that diffuser frequency. However, when you propagate that out to the observer and we're looking at a full integration of the full solution, we can see this is a polar plot showing the directionality of that noise, and you can see the dominant frequency is that blade frequency from the impeller, and the red, green, and black are from the other frequencies, and you can see they are all equally represented in this plot. So even though you don't see the pressure signal of that diffuser, it does have a component to the noise that's observed upstream. You can also see in this plot that there is a directionality to that noise that shows up, especially in the harmonic of that blade passing frequency. So to conclude, we did some study analyses first to show the non-uniformity of the flow coming in, and we discovered that the design of that inlet affected the flow angles and pressure in the impeller eye. We did transient analyses, both single phase and cavitating, to get a more accurate performance of the pump. We were able to analyze the pressure fluctuations primarily at the diffuser, the impeller blade frequency along with its harmonic. And we also looked at comparisons of the transient model with and without cavitation. And what we were able to determine is that the cavitation was not a primary source of the noise. However, it did introduce some compliance into the system that actually affected the amplitude of the fluctuations and reduced the noise level some. We did an acoustic analysis to predict what the noise was from an upstream observer, and we're able to pull out the source of the noise with respect to the unsteady fluctuations in the pump system. So performing this simulation, of course, generated a large amount of data, and
being able to quickly navigate through all of that data and pull out some of these features requires some pretty powerful post-processing techniques. So at this point I would like to pass it over to Kevin, who's going to talk about some of the features of Nsight that can assist in a case such as this. Kevin?
Okay, thank you, Jeremy. Let's go here, advance the slide. So I'm going to talk a bit more about the post-processing involved with these types of cases and illustrate some of the unique capabilities of Nsight with regards to this particular case. The first thing was the use of rigid body motion. This particular solution has either a fixed grid or was solved in a multiple rotating reference frame. So you may have a transient set of solutions or even a steady solution, but there is implied motion, and in this case rotation. Nsight can actually handle and automatically rotate that for you. We have something in here called rigid body motion, where we'll actually pick up and specify a center and an axis for rotation, as well as the speed, and we'll, in this case, since it was transient, we picked up the number of time steps and the total time automatically. And what this does is it allows Nsight to apply Euler transformations to the grid in sync with the transient moving of the solution. So we can correctly integrate path lines. We can visualize the rotating geometry automatically. And since there's a single mesh, there is very little overhead for this. It doesn't actually cost you any in terms of CPU or memory to do this. So you have a much more rich presentation of the solution. So what does that look like here? In this case, you'll see that the pump is rotating automatically, as well as the variables in this case updating on the geometry as we go through. Let's see if I can play this again here. So the geometry is rotating automatically, the variables are updating, and this is all synchronized within Nsight using the rigid body motion. There's only one copy of the grid here, so we haven't had to duplicate any sort of grid for this rotation. We simply apply Euler transformations. Oops, let me go back here for a second. So the other aspect of looking at a complex geometry like this is trying to look at the model in its complexity. In this case, we have curved geometry. We have a hub and a shroud which are not aligned with a particular axis or have a particular curvature to them. So Nsight has this ability to create curved clip planes. This clip will actually follow the wall and the curvature of both the hub and the shroud. We can still use the click and go capability to actually move dynamically through this range from hub to shroud. And we can visualize the data in real time as we move up and down through that percent span. We can also use this clip to quantify variables on. So not only from a visual aspect, but also from a quantitative aspect, we can use these parts to quantify the solution here as well. So this is particularly useful in these type of turbine blade passages or impeller regions, or even curved pipes. Being able to pass a section plane that follows the curvature of the pipe is actually quite handy to understand the flow field as you go through that particular complex geometry. So in this case here, you can see I'm going to move the mouse left and right, and as I do so, that clip plane is actually moving up and down from hub to tip, and all the variables are dynamically adjusting as I move that. So that's a useful way to interrogate the geometry and look at the results in a complex flow field. Another aspect here is actually being to quantify a variable on here. In this case, we've quantified the variable, in this case average pressure. So we can play this again here. We've quantified average pressure on this clip plane, and then as we sweep that clip plane through the range of span, we're actually recording off automatically that value and presenting it in a graph. So we have this graph which is automatically generated as we move this clip plane through, and in this viewport here we can see the location that clip is actually making through that particular pump region. this impeller region. So another aspect here is to query variables on a particular section. In this case, we use that same curved clip plane, and we've actually intersected the blade. And along this blade now, we have an intersection which goes from hub to tip, and we are plotting the pressure along that particular cross-section. So we have a sort of quantifiable information on that particular section cut. And as we drag this clip up and down, this value will dynamically update as well. There's no need to do anything. EnSite handles all this behind the scenes. So this actually is automatically updated with both time and location. And at any point, we can actually just do a right-click on this query and copy the data right out to Excel should we want to have this data in a format which we might deal with in other manners. So here's a little example of that clip plane moving through space. We're dragging it from hub to shroud, and in this case we are actually going through and querying the variable as we go. Let's try to get that to play again here. So as we drag this clip plane up and down, we are changing the span location of that clip, and we can see that the pressure is dynamically updating as we drag that from its hub to tip. So in conclusion, we have this complex solution that we'd like to use a powerful post-processor on to grab out and extract out the information we need. We've been able to utilize rigid body motion to automatically rotate the model. This also helps with the integration of path lines through that transient domain. So if you have fans or pumps, we can automatically update and integrate correctly for path lines. We can use a profile to control the curved clip planes. So we can have these dynamic curved clip planes that we can now drag and pull through the domain and interrogate on complex geometries. We can also query and quantify the variables as we go and show those in an interactive manner as well, so we can get both visual and quantitative information out dynamically in EnSite through this large complex model. So I'd like to thank you for your time today. We hope that we've been able to impart some key ideas regarding using Pointwise, Crunch, and EnSite for complex models. The video for this webinar will be available shortly on both these two links here. Check in probably a few hours and we'll have this webinar updated for these two links. So feel free to pass on that link to colleagues who perhaps weren't able to attend and had information about that. Also, please find our contact details down here should you have any questions. Travis, Jeremy, and myself here are listed. So any additional questions, feel free to contact us directly. So I want to thank you for attending our webinar today. We'll switch over to our Q&A session here, and I'll hand back to Travis for the Q&A session.
All right, so you guys can ask questions now in the Q&A dialog box. I see a couple. Where can I download the seminar? Kevin just pointed that out on this slide, so you can copy down those links, and we should have that updated shortly. Are there any more questions? I'll pass them to the appropriate person as they come up.
And again, feel free to contact us afterwards at the emails below, and we'll be sure to respond to any questions that might come up later as well.
Okay, we got one question. This is, what turbulence model were you using for cavitation calculation? Jeremy?
I believe we were using a K-epsilon turbulence model, but I can double check on that and get back to you. If you send me an email to shipment@crafttech.com, I can double check.
Okay.
Double check that.
Another question, what is the RAM requirement, memory requirement for running a calculation like this?
I'm not aware of the exact number. Of course, that depends on the size of each of the solver modules. This was run on a Linux cluster, and typically we have, for example, on a Linux cluster that might have 8 nodes or 8 processors per node, we typically will have 8 gigabytes of RAM for each of those. And I believe this case was pretty large and probably ran on 64 processors, somewhere around there, and it would have fit within the memory requirements for that. I'm not sure an exact number.
Okay. Another question, we'll just kind of stick along the performance questions for right now. One of them was, what were the computer specs used for the meshing and simulation? We got that for the simulation. As far as the meshing, do you have any specifics about what machine you were using to generate those grids?
Sure. It was probably a PC workstation. We have quad-core Dell workstations that have anywhere to 4 to 8 gigabytes of RAM.
Okay. Okay. And then he asked the same another question was, does Pointwise have any parallel processing capability? No. For some of our structured techniques, they'll take advantage of some of the parallel processors out there, like for example our structured extrusion tools or elliptic solver, some of our examine metrics. But the unstructured tool set is not parallelized. This grid was 10 million elements. I loaded it up on my laptop with 8 gigs of memory and a dual-core processor, and it ran just fine. In fact, with my laptop, I'm able to generate up to 80 to 100 million elements. Another question was any specific relation to grid size, and I'm thinking maybe this is along the lines of, was a grid study conducted for this analysis?
There was not a rigorous grid study that was done. However, typically, we'll start a case and look at, are we resolving the features that we need to resolve, and then there's some extra work done on the grid to do that. But of a case this size, there was not a rigorous grid resolution study.
Okay. Another question for you is, let's see, scroll up here. Now the questions are really flowing in. Can you give a few more details about the leakage flow modeling?
Sure. I'm not aware of all of the details that were involved in that. I was not the one that made this grid. I can say that they were very small passages that transported flow from the outflow of the impeller on one hand back up to the inlet, the suction inlet, and also on the other side to the crossover side. They were very tight clearances, and they were very important to get that right, to get an accurate performance of the pump. So there was a lot of care done to make sure there was enough grid in that. If there's any other specific details you're interested in, please contact me, and I can get you answers for that.
Okay. Another question was, how were the different grid modules matched to each other, point to point, or something else? They were all point-to-point matched, I believe, and that was kind of one of the benefits of electing to use a hybrid meshing strategy, correct?
Yes, definitely. They don't have to be. The intermodule boundary condition can handle non-contiguous interfaces, but certainly the accuracy of that interface is better if you have the cell faces on one side of the interface similar in size to the other. So certainly point-to-point match is the best, but in cases where you cannot do that, the interface boundary condition can handle a non-point-to-point matching.
Okay. Okay, here's another question. It says you mentioned all speeds for your compressible solver. What is your recommended range of Mach numbers for the compressible solver?
We've done cases all the way from very low speed, incompressible, all the way up to hypersonic. We have a preconditioned solver, and we can handle that full range, all in the same solution domain.
Okay. Can GPU cores be exploited for a simulation of this size?
We are currently interested in that. We did not utilize anything like that in this simulation, but certainly there are benefits you can have to do that, and we are looking at that with our solver. And again, if you want any more details on that, you can contact me directly.
What about on your side, Kevin?
We pretty much sync all the GPUs with graphics tasks rather than sort of computation CPU type tasks. We've seen some GPU-related speed up with regards to structured grids per se, but not necessarily in the unstructured world. And most of our stuff we deal with as an unstructured manner. So we typically don't find much for the GPU. But having said that, we will pretty much soak the graphics card capability for graphics stuff rather than any particular CPU-related items.
Okay.
I just add one more thing with the question about the parallel processing. Kevin, do you want to mention anything about your Insight's abilities with that?
Yeah, we can go parallel across the heterogeneous system through partitioning the model into n number of pieces and having n number of servers actually handle their own piece of the model. So we do that either as a automatic decomposition, if you like, or in some cases we can handle the pre-decomposed data that you may have from your solver, and then each server could grab either one collection, or sorry, one domain or a collection of domains to handle it in parallel. So Insight handles parallel across the heterogeneous network that way, as well as threading. We have multi-threading enabled even in the Insight standard. So you get where computations have been threaded, you can take advantage of the multiple threads that are on your system as well. So both in a macro and a micro scale.
Okay. Have a question asking, how long did the total calculation take?
I don't know exactly this case in particular, but other similar cases which involve very similar setup. We were looking at, there was a requirement to do multiple cases with different conditions, and I believe once the case is going, we can do a full unsteady analysis. I believe a day or two. We can turn those around, or less.
Okay.
It all depends on. We run these on Linux clusters, anywhere from 64, 128 processors, and usually we can, within 1 week, we can turn around a full set of unsteady cases.
Okay. Kevin, here's a question for you. It says, can Insight compute the statistics of the cavitation bubbles, for example, size distribution?
Yes, so we can, from a temporal point of view, we can query the data over time and pull out statistics from the temporal data. We can also go through, and with the ISO surfaces, we could probably create an ISO volume around each one of the cavitation bubbles and look at the location of them over time and keep track of their position or size as either a volume or an area. But we can also deal with the transient variables and look over the whole time domain to extract out variations, statistical means, deviations, and so forth, right from the variables themselves.
Okay. Jeremy, here's a couple of questions for you. One is, how do you compare your cavitation number with experimental data?
Yeah, we've done a lot of rigorous validation of the models where we look at some of the experiments done in the literature. We look at cavitation size where you can track that, as well as pressure, those kinds of things. I can probably get some better information for you on how we validated those models against experiment. If you're interested, please contact me. I can get you some better details on that.
Okay, and the second one is, how do you deal with shock waves?
Well, in which way? In terms of the cavitation modeling? Was this from the same question?
Same question. I think just in general, asking about Crunch CFD.
Right. Well, we can capture shock waves in the in the solver very well, as long as you have the grid resolution to handle that. And certainly if something like that were present in this case, that would have affected the acoustics.
Okay.
If you can give me more specifics of your question, I can probably get a better answer to you.
Okay. Are there any more questions? This one asks, compared with the cavitation bubble size, is the grid size larger or smaller?
Compared to, well, the grid, if I understand the question correctly, the mesh resolution in that region will affect the accuracy of capturing that. You have to have a well-resolved grid in that. So there are many more cells in that region than the cavity bubble. You're resolving both the interface of the gas to the liquid, as well as the volume that entails. So certainly, if your mesh resolution is not adequate at the leading edge of the blade, there we would not get an accurate resolution of the pressure drop there, or the phase change.
I think you'd probably need an order of magnitude more elements than you think your cavitation bubble size is to begin to capture that existence and the size and shape of it appropriately.
Yes. Yeah.
So.
What those pictures are showing are isosurfaces of the vapor fraction, which is how we're displaying the bubble.
Okay. Here's another question asking us all to compare our software with similar software, and I think probably that question is better answered. We can do that via email. You can just contact any of us, myself at Pointwise, Kevin at CEI, or Jeremy at Graphtech, and we can talk to you about that. Okay, if there are no other questions, then we'll end this webinar. Again, thank you all for attending. The videos and the information will be up on the websites that you see on your screen. And again, if you have any other questions, please feel free to contact us. So thank you all for attending.
Thank you.
Thank you.